Section 12.4 is applications of double integrals. So we'll mostly be looking at a density function, which is, if we recall, density is mass divided by volume or mass divided by area, depending on what we're looking at. So we're mostly going to consider a lamina, which is a thin disk or thin planar region. We'll assume that up and down in the z-axis, the density is more or less the same, or this thing is so thin that there's no real need to consider the z-axis. So planar regions, and we'll essentially look for is the entire mass in such a lamina, and then we'll look at the center of mass of such a thing, the balance point in some sense, if we were to balance this on a single point underneath it. How to calculate where that point would be. And then lastly, we'll talk about the second moment, or the moment of inertia, and that's the tendency of the body to rotate about an axis or to resist rotation about an axis. So first off, let's calculate the mass of a lamina, or one of these thin plates. Recall that rho of xy, so we will let rho of xy represent the density of this lamina at the point xy within D. Okay, and that's equal to the limit of delta m over delta a, where m is the mass and a is the area. So we'll use this idea. This is taken as the dimensions of the rectangle, the tiny rectangle within D, approach and containing the point xy, go to 0 or approach 0. So we're shrinking some tiny little rectangle in this lamina, and that's what the density is actually equal to. So we can approximate the mass before we take this limit then as rho of xij, yij, so rho of xy essentially we'll say times the area of that little rectangle, and that's approximately equal to the mass at some given point. Now, what we'll do overall is what we see in this formula here is that we're going to sum over the i's and j's, so we're going to sum over all the rectangles. The density of all points xij, yij, stars, which are within each of those subrectangles that we divide D into. We're going to divide D into k times L subrectangles, reflected here and here. And the mass of the entire lamina is the sum over all of those rectangles, and it's the sum of the density of each rectangle times the area of each rectangle. Of course, density times area will be mass in this case, okay, for a planar region. Okay, so expressed as an integral, this double Riemann sum, we take the limit as the dimensions of these rectangles go to 0, subrectangles go to 0. We'll get infinitely many of those subrectangles with infinitesimal area, and sums become integrals over D, and we have our continuous function rho of xy, which we're integrating. So mass is equal to the double integral rho of xy over the region D. So to see an example of this, we're asked to find the mass of the lamina that occupies the region D given below and has given density function. So here's our given density function, and here's our region. We get lucky with this one and quite a few of them. This is a rectangular region, so it's a fairly straightforward integral. We're going to leave it that way because we don't want to cloud these applications up too much. So the mass formula, so double integral of the density times the area, and set up our limits of integration. It looks like we're integrating with respect to y first, reflecting those limits of integration, then with respect to x. So being sure we do that in the correct order and apply the correct limits of integration, we get the following: integrating with respect to y, holding x constant from 0 to 1. Y now leaves our integrand, and we're left with a function of x. Simplifying that, we have the following polynomial: integrating with respect to x, straightforward antiderivative of a polynomial, evaluating from 0 to 3, and we've got our mass is equal to 13. Okay, so a nice clean example use of this formula. So the mass of this, whatever this lamina looks like, I'm sorry, whatever this lamina looks like, with this rectangular lamina, actually, we know that it looks like a rectangle, goes from x equals 0 to 3 and y equals 0 to 1. With density function, its total mass is 13. We'll make use of this value in just a little bit in another example. Another way to look at these this density application is to also think of total charge being mass, or playing the role of mass. And if we have a charge density or a distribution of charge density over a region D, this is an electromagnetic example, the total charge Q of this region D would be equal to the integral over its charge density function. Okay, so say in a physics 2 or an electricity and magnetism course, you're interested in finding the total charge of a given region, and you knew the charge density, this would be the way to go as well. Yet another one is to consider Q as probability of something, and then this could be a probability density function. In other words, it's essentially the probability that something is in a given region X, Y. If we integrate over some subregion there, we'd get some probability that something is in this region D. So that's a probability example as well. The book only does mass and total charge as the examples, so we'll stick with those in text. Okay, so the next thing to consider is moments and centers of mass. We can calculate the mass of a lamina now, so let's see how much further we can take that. So let's recall some discrete cases, both on the x-axis or in one-dimensional space, and then in the plane with the xy coordinate system. So on the x-axis, to find the center of mass along some axis, so along some line, we've distributed n masses with each with respect to mass m1 through mn and position x1 through xn. So they've all been distributed along this x-axis, or this single line here, and we know that x bar is the center of mass for this collection of point masses. So in other words, it would be the balancing point for this collection of masses if we're able to calculate it. If you recall from either chapter 7 in the textbook, going back to that, applications of integrals and integration there, this derivation for finding the center of mass in a discrete number of point masses distributed along an axis, we can, you can either see it there or you recall it from a physics course, physics 1 course likely, where you're doing Newtonian mechanics. And it's the sum of mi times xi for all n of these masses in their positions, divided by the sum of all the masses. And this is exactly how you calculate the center of mass for that collection of point masses. Now, in the by the way, this mass times position, so any one of these masses times its position is called the moment of that mass. Okay, so we'll discuss the moments of these mass throughout the rest of this. Now, if we have a region in the plane, or if we have n point masses in the xy plane, they might be distributed something like this. I've done this somewhat arbitrarily, x1, y1 with mass m1, x2, y2 with mass m2, and dot, 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 up to get up to xn, yn for n point masses distributed throughout the plane with n different masses. And of course, this distribution of point masses will have a center of mass as well. It's a point x bar, y bar. And to calculate it, it's quite similar to what we did above, only we do it twice. We do it once for the x coordinates, we do it once for the y coordinates, and in both cases we still divide by the total mass, the sum of all the masses. And that's how we find the center of mass in the plane for discrete masses. And these are not connected to each other, or we could think of them as being connected by weightless thin rods. And that could be how we discuss their connection for their balancing point or their center of mass. Now, we'll represent m as just this total mass, the sum of all the point masses in the system. M sub y will be, this is the moment about the y-axis. So in other words, this is essentially finding the balancing point about the y-axis. That's x bar, right? So, and it's opposite for the moment about the x-axis. That's balancing along y values on either side of the x-axis. So that's why the moment about the x-axis involves y. Similarly, for the moment about the y-axis involving x instead. So with these things defined, and this idea of how to find moments and centers of mass for points in the plane, we can now extend this to the continuous case of a lamina D. So the idea, we want to find the center of mass of a lamina D, which has continuous density function, again, rho of xy. So that looks familiar at least. And the idea, of course, is to divide this lamina into subregions, subrectangles, with a point inside there that's xij star, yij star, that will always remain in that rectangle no matter how much we shrink it. So that always tag that rectangle at that point. And in order to calculate the moment about, we'll say the x-axis first, we'll use this formula here for each of these little subrectangular regions. So it's the density function at that point times the area of that subrectangle times yij star times the y coordinate. Again, that's the moment about the x-axis. So that's one of these values that would correspond to one of these values over here. Okay, just one of these moments, mi, yi. So of course, we'll sum up each of those moments about the y or the x-axis. So we'll sum up all of these here about the about the x-axis, and we'll need to do that for x coordinates as well, because those are spread out. Because we're spread out all throughout the region, and we have rectangles side by side all throughout this lamina. Okay, but we're only going to multiply them by this yi sub j, because that'll give us the moment about the x-axis. When we do so, we have a double sum to sum everything up. So this is here. The exact moment about the x-axis will take the limit as the dimensions of these rectangles shrink to 0. And we have yij star times the density function at each of these points times the area of each of these subrectangles. And this is in the limit equal to the integral over the lamina D of y times the density function, rho of xy. So we do the same thing to find the moment about the y-axis. Again, we're balancing over the y-axis, so those are x coordinates, x values that we're interested in. We limit the dimensions of the rectangles to approach 0 as we sum up the masses of all of these rectangles. Now again, the masses are given by this expression right here, then times the position, and that's the moment again, right? So it's this x times the mass is the moment. And that's why this formula, that's how it connects to what we did previously. It's why it's set up the way it is. In the limit, of course, this is equal to the double integral over the lamina D of x times rho of xy dA. Another way to see that things are fitting is here's position x times rho times area is mass. In some sense, even in this infinitesimal case, we can still see that the products are lining up the way we'd like to see it. So rho density times area is mass. Position times mass is moment. So let's use this one as well. We actually summarize some of this and define what our center of mass is. So our total mass, m, we've got that from before, and we'll need that because what we've done in the past is divide our moments, m sub y about the x-axis for a system, by the mass to get our center of mass in the x component, in the x coordinate. Okay, so we take the moment about the y-axis divided by m. That, as in terms of what these things are, remember that the moment about the y-axis is given by this double integral, and this is just our division by the total mass. So we've got that for x bar. Y bar is very similar, the moment about the x-axis divided by m, and that looks just like what we've seen previously. All right, in the moment about or for the x coordinates center of mass. or the x-coordinate of the center of mass. Okay, so the example below recycles the problem we were given before, only now they ask us to find the moments and the center of mass of the lamina which occupies the region D, which again is the region we looked at in the previous example, just to simplify our work and shorten the time here. And given density function, same density function we saw in the previous problem. So this is the exact same lamina, only now we're asked to find its moments about the y-axis and the moment about the x-axis, as well as the center of mass. So the total mass was 13. That was from our previous example, previous work. Now we set up the moment about the y-axis. Now remember, that's the double integral of x times rho of xy. Order of integration is not necessarily important here. We have a rectangle, so that's pretty easy. It looks like we're going 0 to 1 is the y component, so we're going to integrate with respect to y first, apply those limits of integration. We arrive at this, which is essentially a Calc 1 integral, power rule, and integrating from 0 to 3. And the rest of the details on this one are pretty straightforward to follow, but we arrive at 105 over 4. Okay, the moment about the x-axis, again, that's y times rho of xy, y times the density function. Again, it looks like we integrate with respect to y first, then x, and y times this function, or this rho of xy function, gives us what we've got highlighted below. And integrate with respect to y, apply limits of integration. Integrate with respect to x, apply limits of integration. And we have our value of 27 over 2 for the moment about the x-axis. So x bar, y bar, the center of mass, is given by, well, we take m is 13, and it's the moment about the y-axis over 13, or over our mass, moment about the x-axis over our mass, and we'll see that we multiplied both of our moments by 1 over 13 to arrive at this center of mass here. So 105 over 4 times 1 over 13. Similarly for the y component of the center of mass. Next is the moment of inertia. So the moment of inertia is the tendency of a particle some distance from an axis to rotate or to resist rotation. So what we've got below is, again, as we're going to consider a lamina D. We won't go through all the details of the discrete case because the work here is very similar to what we've done in past problems. Only now, since our second moment is calculated as m times r squared, where r is the distance from the particle to the axis. Well, if that were the x-axis, then it would be a distance y from the x-axis, right, above or below it. Okay, so that's why this y shows up. It's squared, so that's why it's y squared in both cases. And again, this is all the subdivision and the double angle, or sort of the double sum of all these subrectangles with the m times r squared formula. This is playing the role of r squared. Density times area is the mass for this lamina. We shrink the dimensions of these rectangles to 0, which are via the limit, which yields the double integral y squared rho of xy dA. So it's just essentially an integral formula to us at the end of the day. So this would be the moment of inertia about the x-axis, tendency to rotate about the x-axis or resist rotation. I sub y is the tendency to rotate about the y-axis. And again, we see the swapping of roles here. X squared is there. X is the distance from the y-axis, so that's why that's labeled as is. And there's also a new one, the moment of inertia about the origin, or the polar moment, which is given as follows. X squared plus y squared times rho of xy dA. So our last example is to find the moments of inertia of a homogeneous disk D with density rho of xy equals rho. So it turns out our density is constant. It's not actually a function of x and y when we look at the right-hand side. This, the disk D has center at the origin and radius a. Homogeneous means that up and down in the thickness of it, it's the same. So there's no reason to consider the z-axis. That's why that word shows up in there. We weren't going to do that anyway because we haven't done so far. So it's just easy for the student to assume that. Now, rho of xy equals rho. We realize we're dealing with a circle. We're going to integrate over this circular disk. So why not use polar coordinates? That'll simplify our work here. Now, what's nice is that rho of xy equals rho. There's no function of x or y on the right-hand side explicitly. It's a constant function rho. So when we convert it, x equals r cosine theta, y equals r sine theta, we just end up with the same function in r theta of rho. So that's a nice easy conversion for the problem. Now let's see, the region that we're looking at, this goes from 0 to 2 pi. So there's theta and our limits of integration, 0 to 2 pi. And now we've also got the radius goes from 0 to a. So there's our limits of integration for the radius. And now the one thing we need to remember is that this integral is over the region D. It's, in the case of the moment about the x-axis, I sub x, it's y squared rho of xy dA. Now we've expressed this is the general integral for that, double integral for that region. What we have below is this is y squared, r squared sine squared theta. So we do introduce some complication into the integrand thanks to the formula itself, but the density function being constant has really done us a favor because this function is only rho. It's a constant. In fact, we'll even move it outside of the integral once we get going on this problem. So don't forget that this r is part of the polar integration over a polar rectangle or polar integration of polar coordinates. So we end up with r cubed sine squared theta, dr d theta in our integrand, and we're off and rolling with a polar integral. We have 1/4 r to the 4th evaluated from 0 to a is just 1/4 a to the 4th. That's a constant, so we'll move that out as well, simplifying our integrand even further. Rho a to the 4th over 4, and now we have the integral of sine squared theta from 0 to 2 pi. Well, the integral of sine squared theta, either use the half angle identity, sine squared theta equals 1/2 minus 1/2 cosine 2 theta to swap it out and integrate the right-hand side, or you just remember that the integral of sine squared theta, or look it up from a table, that it is equal to what we have on the next line in the equality. And that's 1/2 theta minus 1/4 sine theta from 0 to 2 pi. Evaluating at those limits of integration yields just pi from evaluating the function in brackets. And our moment of inertia about the x-axis is pi over 4 rho a to the 4th. Again, a is the radius of this. So the further we are from the center, the larger this moment of inertia, or the second moment about the x-axis is. We'll talk about that maybe a little bit in the end of this. So the moment about the y-axis, the only difference is we have x squared here now, so that changes that what was a sine squared above to a cosine squared. Everything else is as would be expected, our density function, r from the polar integral formula. And integrate with respect to r to yield this. Evaluating at the limits of integration, integrate with respect to theta, very similar to what was done above. Either it's recalled or we use the double angle identity for cosine to get here. And evaluate from 0 to 2 pi. And it looks very similar to what we had above. The function in the brackets evaluated at those limits of integration is just pi. The reader can check that for themselves. And this leaves us with pi over 4 rho a to the 4th. Once again, this is telling us that the further we are from the origin, the larger our moment of inertia is. Okay. So lastly, this is our polar moment, or the moment of inertia about the origin, or second moment about the origin. Remember, it's x squared plus y squared times rho of xy. So here it is in polar coordinates. Now we know something quite nice about these polar coordinates. We can factor out an r squared from these terms. We have cosine squared plus sine squared. That's just 1 times r squared. So r squared coming out of this expression times r is r to the third rho dr d theta. And that's exactly what we see to the right. R cubed rho dr d theta. Again, rho is a constant, so it has little bearing on this on the integration itself. So we'll have 1/4 r to the fourth evaluated from 0 to a. That's 1/4 a to the fourth times rho. And this is the easiest integral of them all, really. Now we integrate this expression, which is just a constant in the integrand with respect to theta. And we arrive at that constant times theta evaluated from 0 to 2 pi, which is exactly this expression here, 2 pi minus 0. It's standing in place of theta for the evaluation of theta at those endpoints. And the result of that is pi over 2, a to the fourth rho. Again, a is the radius, and the fact that that is a to the fourth tells us that the further we are from the pole, or from the origin, or from either of our axes, the larger the second moment, or the larger the moment of inertia. This can be thought of as, if this were a wheel, the further we are along this wheel or disc that's spinning or whatever, the harder it is to turn a mass of equal size. So if each of these dots was a mass of equal size, the further we get away from the origin and we want to rotate about the origin, the more resistance there is to that, the more force is required to overcome the fact that it's not moving or to stop it. Okay. So that is the second moment, and that concludes everything we'll do in 12.4 as well. So the problems here should be fairly straightforward. There are fewer than other sections, but it will take a little practice just to get the hang of these integral formulas.